Hi, I'm Nick Moffett with Verisurf Software. Today I'll show you how to use the FARO Vantage Tracker with Verisurf's metrology software to align, inspect, build, analyze, and reverse engineer parts and assemblies. The FARO Vantage is a very compact laser tracker. It's 16 inches tall and weighs under 28 pounds. The tracker has a measuring volume of 160 meters or 80 meters in any direction. An IP52 water and dust rating allows it to operate in a wide range of conditions. FARO's true ADM technology improves dynamic accuracy and eliminates the need for interferometry in most applications. The multi-view camera system efficiently locates targets and enables Smart Find for rapid beam pickup. Finally, the tracker offers integrated solutions such as a weather station and a precision level. These are just some of the highlights of the FARO hardware. Next, we'll take a look at the software. Verisurf's metrology software is built on a CAD platform, giving it full CAD design capabilities. CAD is required for reverse engineering, but it's also very helpful when inspecting complex parts. For example, we can analyze a model, we can pull dimensions from a model, we can even manipulate a model. In addition, tools such as colors, levels, and attributes allow us to manage large part assemblies. Verisurf integrates design, inspection, layout, analysis, and reverse engineering all into a single application. Finally, Verisurf is designed for both print and model-based workflows. I'll continue by loading a model of our demo part. Verisurf reads all popular CAD file formats such as CATIA, ProE, NX, etc. in their native format. This avoids the limitations of neutral formats such as STEP and IGES, which Verisurf can also read. When we open a native file, Verisurf saves it in the MCX format and leaves the original file intact. All of the data, including the model, the measurements, the analyses, and the reports, are stored in a single file to simplify handling and avoid data loss. I'll choose the MCX format and open our demo part file. The part is in place and the model's loaded. In the next step, we'll align the laser tracker to the demo part. After we load a model, we typically align the device to the part so we can get real-time feedback on tolerance condition. We'll use AutoAlign since it's the easiest way to align to a model. We start by placing alignment targets on the model to control the orientation of the part. Since the FARO Vantage is in front of the table, we'll place the alignment targets with a clear line of sight to the tracker. I'll start by selecting an appropriate graphics view for the targets. I'll choose Create Target and place alignment targets on the top, front, and side of the model. Since I want the camera view to match the graphics view, I'll go back to our original orientation. Before I run the alignment, I'll edit the targets and enable Use Smart Point. When we use the Smart Point method, Verisurf automatically records the target location when we hold the SMR stable on the part. I'll choose Run AutoAlign and measure the targets as they're highlighted. When the last target's measured, Verisurf displays a result dialog. We can review the results and modify the fit if necessary, but since the results look good, we'll choose to accept. When we do, Verisurf runs Inspect Build so we can verify the alignment. The small deviations we see as we move the probe around the part indicate a good fit between the part and the model, which means the alignment is correct. This final check is a validation of the whole AutoAlign workflow because it shows that we have the right part, the right model, and we didn't make any measurement mistakes. AutoAlign is a very powerful tool for model-based alignment, but it's easy enough for beginners to learn and to use. In addition, the results are easily verified using Inspect Build mode. The FARO Vantage is now aligned to the part. In the next step, we'll check surface profile. In the previous step, we used Inspect Build to verify our device alignment. Inspect Build is a special measuring mode that displays in real time the deviations between a part and the corresponding features in a CAD model. When we're inspecting a part, the deviation reflects the material condition, and when we're moving a part into position, the deviation shows us how far to move, and the arrow indicates the direction. Since the Vantage tracker is already aligned to the part, when we inspect profile, we'll assume the deviations are due to machining errors in the part. I'll start by measuring deviations in single point mode. Notice how the deviations are represented using arrows and deviation text. Next, I'll switch to continuous mode and scan the part. When I press Escape, Verisurf creates an analysis object in the data tree. If I highlight the analysis, we can see the distribution of deviations in the color bar. If I double-click the analysis, we can change the way the deviations are displayed. For example, we can add borders, we can change from lines to spheres, and if we enable Use MBD Tolerance, Verisurf analyzes the data according to the surface profile callout, otherwise it uses the global profile tolerance. I'll switch back to our original display, save the results, and then add balloons to annotate the deviations. Choose Balloons, Auto Add, and apply it to a random 10 deviations. We can arrange the balloons manually if necessary, but for what we're doing, this should be sufficient. I'll save the results, highlight the analysis, and then create a report. I like the screenshot on top, so I'll change the order. I'll also access Settings and change the logo from Verisurf to FARO. We have a number of options for the report: PDF, Excel, PowerPoint, Word, etc. I prefer PDF, so we'll leave it there. When we create the report, we see the FARO logo in the header, we see the annotated deviations in the screenshot, and we see the details in the body of the report. We've just seen how to use real-time deviation analysis to check surface profile. In the next step, we'll use it to position our demo part. When we use build mode to position a part, we assume the form of the part is good and the deviations are due to errors in position of the part. We refer to this use of real-time deviation analysis as build mode because we often use it to build fixtures and assemblies, but we can use it anytime we want to position an object in 3D space. We'd normally start by aligning the device to the basis of the CAD model by measuring features with known CAD values. We did this in AutoAlign. We'd then build parts into position by moving them to their nominal locations. Since the tracker is already aligned to the basis of the CAD model, we'll simply move the part and use build mode to put it back into position. I'll start by selecting and building to circles first because that's a quick way of getting the part aligned. I'll place the SMR in one of the holes and move the part in the direction of the arrow. I'll then move to the second hole, repeat the process trying not to move the first hole. Check on the first one, make a correction. When I get close enough, I'll cancel the selection. I'll display the GD&T or MBD, and then I'll build to surfaces. I've displayed the MBD so that we can use the surface profile tolerance to control the build tolerance. In other words, as long as all of the surfaces are located within their profile tolerance, we'll consider that the part's in the right location. We don't have to build to 0, we just have to get it within tolerance. This is already much closer than I need for this step because in the next step we want the part out of alignment. Green everywhere, we'll call it good. So this is a very simple example of the build process. Setting a part or a detail in 3 dimensions is much more complicated, but the process is the same. The part is now essentially aligned. We'll kick it out a little bit more because we want it that way for our next step. We've used inspect mode to check our part in real time. In the next step, we'll perform a similar analysis, but we'll start by measuring point clouds. I'll begin by running inspect mode so we can verify our device alignment. We know the part is good because we've already inspected it, and we know the alignment's bad because we left it that way at the end of our build demo. I'll switch to point mode and scan the part. We're not getting real-time deviation analysis, we're just collecting raw probe center data. When I'm done measuring, I'll press Escape, select the Analysis tab, and analyze the point clouds. The results are similar to what we saw in Inspect mode, but the deviations are much larger because of our intentional misalignment. I'll hide the analysis, select the clouds, and run Best Fit. Before I run the fit, I'll analyze the data for a baseline analysis. When the fit is complete, the results show the part is good, similar to what we saw in Inspect mode. I'll choose OK and accept the best fit. If I toggle between the before and after, we can see the improvement. And if I select the Measure tab and run Inspect mode, we can see from the deviations that the best fit is applied to the device alignment as well. Inspect mode, which we saw earlier, and analysis, which we just performed, are very powerful tools for model-based inspection. In the next step, we'll measure and analyze prismatic features. All of the workflows we've seen so far have been model-based. We've aligned to a model, we've inspected and analyzed to a model, and we've built to a model. Next, we'll discuss print-based inspection and reporting of prismatic features. I'll align to the part frame shown here, but we're not using a model, so I'll open a new file. I'll start by measuring a plane in 2 circles for an alignment. For the circles, I'll use a pin nest. Verisurf automatically compensates for the radial and axial offsets. Next, I'll run Feature Align. We can see that the origin is located at the center of the large circle, and the x-axis runs through the small circle, so our data is aligned correctly. If I place the probe at the origin, we can see the device is aligned as well. At the beginning of the presentation, I mentioned FARO's Smart Find as a way to pick up the beam if you lose it. Before I continue measuring the part, I want to explain how that works. If I break the beam, I have only to gesture to the tracker and it automatically locks back onto the target so I can continue measuring. I'll continue by measuring features starting with the small circle at the center. Next, I'll measure a slot. I'll place a tooling ball into one of the holes so that we can measure a sphere. Next, I'll measure part of the hole pattern using single point mode. Finally, I'll switch to point mode and measure 4 points on the left plane. I'll switch to continuous mode and measure a cloud on the right plane. I can take the points and fit them to a plane, and I can do the same with the cloud. All of the features that we've measured so far appear in the data tree. If I select a feature, I can see its characteristics such as its position, size, shape, form, etc. If I select 2 features such as 2 points, I can see the distance between them. And if I select 2 features such as planes, I can see the angle and distance between them. We've seen how Verisurf and the FARO tracker measure prismatic geometry. Next, we'll analyze and report the results. We briefly saw the report manager when we reported our inspection results. Next, we'll take a closer look as we analyze and report our measured features. For the report, I'll highlight the planes and the circles. When I choose the Reports button, the features are displayed in the Report Manager. If I highlight a feature, I can see its characteristics in the Details pane. We use these fields to enter the nominal and tolerance values. I'll enter the nominals for Circle 3 so we can report its position. The toolbars allow us to add nominal features, to construct features, and to add GD&T callouts to the report. I'll use them to construct the plane and the circle through the hole pattern. I'll start by selecting the circles and then choose Construct Plane. With the circle still highlighted, I'll choose Construct Circle to find the center of the hole pattern. I'll then rename it Center. Next, I'll construct lines from the center to circles 4 and 5. I'll then highlight the lines, calculate their angle, and enter the nominal value. I'll find the distance from the center to circle 4 and enter its nominal value. I can select the end planes and calculate their parallelism, and I can find the concentricity of the center to circle 1. Finally, I'll report the position of circle 3. I want only the final values, so I'll highlight them before creating the report. When I do, we see the FARO logo in the header, and we see the details in the body of the report. I referred to the measurement, analysis, and reporting of prismatic features as a print-based workflow, but it works equally well, if not better, with a model. For the final example, we'll look at reverse engineering. Verisurf's reverse engineering tools allow mixed modeling with NURB surfaces, meshes, prismatics, and solids. Moreover, we can take advantage of the many CAD tools inside Verisurf. For this demo, I'll scan and then surface contour on the demo part. Unfortunately, there's not a lot to work with on this part, so I'll use the Verisurf demo part instead. To begin, I'll open a new file and align the device to the part. Once the features are measured, I'll run Feature Align. I've applied offsets in X and Y so that all of our data is in the positive XY quadrant. I'll accept the alignment and then scan the top of the part. When the measurements are complete, I'll choose the Reverse tab, highlight the cloud, and choose Patch. The parameters allow us to control the accuracy and complexity of the surface. I'll verify that the probe offset is correct for an SMR and then create the surface. When the results are displayed, we can see the values are in range, so we'll accept the result. We now have a surface that the parameters indicate is good, but how can we verify it? On the Measure tab, we can run Inspect mode and compare the surface to the part. On the Analysis tab, we can analyze the point cloud to the surface. The data from the Vantage Tracker is traceable, so this gives us a way to prove the accuracy of our surfaces. This is a great benefit to an integrated metrology platform. This was a very simple example of reverse engineering, but it shows how easy it is to create CAD surfaces and also to verify them. That concludes the presentation. I hope I've given you a good appreciation for how Verisurf Metrology software enables the FARO Vantage Tracker with a complete set of model-based tools for alignment, inspection, tool building, analysis, and reverse engineering. For more information about FARO laser trackers and Verisurf Metrology software, please contact FARO Global Headquarters at 407-333-9911.